Hi, this is Nick Pizzi. Last year I uploaded 35 videos to YouTube that are designed to help water plant and distribution operators prepare for certification exams and to improve your math and science skills that you need in your work. Many of the unit process-oriented videos used examples taken from the operational data of the Lake County, Ohio Aquarius water treatment plant. Some of you got back to me and asked for a video that provides an overview of the whole plant, which you could use as a means of becoming more oriented to the flow patterns of it, and to help understand how these processes were chosen and why they operate the way they do. So this video brings that overview to you. You should be using it as a precursor to the individual modules from last year. And hopefully this will help you in your quest for your next level license exam and for plant and system optimization. So good luck with that, and here we go. So the agenda will follow would be a review of standard engineering factors that Ohio EPA uses to approve the requirements for water treatment plant unit processes, the approval process itself. And in doing so, we'll review the operational steps that are used by water treatment plant operators, specifically at this Aquarius water treatment plant. And we'll compare those operational habits to the approved standards. In other words, do the operators operate the unit processes according to the way they're supposed to be, they were designed. And in doing so, as we go along, we'll review regulatory frameworks that might apply, and we'll work some math problems as we go along also. So what do we mean when we use the term unit process? A unit process in a water treatment plant is a component that has been designed properly by an engineer, has been approved, and it stands for a specific purpose in the overall treatment scheme. It's a very important part of the overall function of the water treatment plant, and it is meant to be operated. That is, an operator should understand how the unit process is supposed to work. It's supposed to be able to measure the performance of that particular unit against the design standards. These operating parameters are very well defined. The success of the process depends on that operator being able to understand the parameters and working within them. The unit process stands alone in its function, but by itself, it cannot produce a finished product without the other processes. They all have to work together to make the finished product of drinking water. If the process itself becomes non-functioning, the product cannot be made, or the quality of the water itself is going to be diminished. It may still meet standards, but it will be diminished. So the performance of the results of the unit process itself can all be measured. That means you can set goals for them, and the operators can then measure the performance of the unit process against those goals. Operators can check to see if those goals are being met and if the process is functioning properly. Now, Chapter 6109 of the Ohio Revised Code provides authorization to the Ohio EPA to safeguard public health by enforcing requirements such as those that are found in the Safe Drinking Water Act. One of the steps that are included would be their review of engineering plans that might be submitted by any given utility. Now, to ensure adequate quantities of safe drinking water are provided, the Division of Drinking and Groundwater staff will review these engineering plans and any other information given along that is pertinent to the proposed public water supply projects. So if a new plant is going to be designed and built, or a component is going to be designed into an existing water plant, the division has to check these guidance documents to be sure that the plans meet certain specifications. One of the standards that they use would be called 10-state standards. We'll take a quick look at that. 10-state standards, officially known as the Upper Mississippi River Board of State and Provincial Public Health and Environmental Managers, provides a list of plan approval and specifications of public water supplies. So it's a Bible when it comes to engineering standards for components of water treatment plants. So the approval process in Ohio goes something like this, and this is going to be very simplified. It's much more complicated than this, but I'm going to make it easy today. So a utility would submit their engineering plans to Ohio EPA for review. Whether they were going to build a brand new water plant or build a process in a water plant, doesn't matter. Those plans have to go to Ohio EPA for review, and when they're submitted, they go into a plan review process. The engineering group of Ohio EPA checks the plans for conformance to accepted engineering standards and guidelines. And as I mentioned, Ohio does allow a utility to conduct special studies for the purpose of gaining design approval of design parameters that are less conservative than what might be found in 10-state standards or other published guidelines. Now, among those standards and guidelines that we're going to talk about today would be rapid mixing, flocculation, sedimentation, filtration, and disinfection for this particular Aquarius water treatment plant. So let's review each of those. Some of the requirements for rapid mixing and flocculation would look like this. Now, for the rapid mixer, Ohio requires a detention time not greater than 30 seconds. And you must have provision for adding your primary coagulant there, and it has to be able to be fed at all times that the mixer is in service. You must have mechanical mixing, and static inline mixing will be considered, but the mixing has to be capable of developing a G value not less than 750, and that G can be determined by jar testing. And mixers, of course, are supposed to be placed as near to the flocculators as possible. For flocculation, you must have inlet and outlet designs that minimize short circuiting, and you have to have a detention time of at least 30 minutes with a flow-through velocity somewhere between 0.5 and 1.5 feet per minute. So that's pretty much slowing things down. You have to make provisions for tapering the mixing energy that you put into the compartments of the flocculator. And the agitators that drive those flocculators have to be variable speed systems and capable of driving the peripheral tip speed paddles somewhere between 0.5 and 3 feet per second. Look at more requirements for sedimentation basins. Designs require detention time of at least 4 hours at the max flow rate of the plant, but lime softening plants with well water sources can be allowed as short as 2 hours of detention time, and that can be negotiated. Water treatment plants can get approval of a lower detention time through demonstration studies, for example, if they're going to put in tubes or plates or something like that. And water plants can get approval of a detention time if the overflow rate is not more than 0.5 gallon per minute per square foot. Inlet devices of basins have to be distribute water equally with uniform velocity. So typically the newer basins that you see coming out, rectangular basins, are going to have a baffle wall, which is going to be so close to the inlet of the basin itself to accomplish this. The flow through velocity shall not be greater than 0.5 feet per minute. We'll see when we go through the Aquarius plant today. The calculations are going to prove to show us a value of 0.75 feet per minute, a little bit faster than what they would allow today, so we can see that got grandfathered in. The outlet weirs or submerged orifices of a said basin has to be installed so that they maintain an even velocity, and they don't want the weir overflow rate to exceed 20,000 gallons per day per foot. Of course, the submerged orifices shall be no lower than 3 feet from the surface and not exceed a velocity of 0.5 feet per second. They have to have sludge removal devices. They have to be capable of removing sludge from all areas of the basins. And the sludge piping shall not be less than 3 inches diameter, with a sample port available for operators to be able to take samples of the sludge. Of course, there's a lot of other provisions for demonstration studies: tubes, plates, solids, contact units, dissolved air flotation, all that kind of thing. We're not going to get all of that today. If we look at some of the filtration requirements for filters in Ohio, the EPA makes provisions for many kinds of filters. Rapid rate filters, pressure filters, slow sand, all kinds of filters, membranes, that type of thing. But we're going to stick to rapid rate dual media filters here today because that's what the Aquarius plant has. There has to be at least 2 of them, and where there are only 2 filters, each must be capable of handling the max flow rate. So in other words, you're a small plant, you have 2 filters, one of them has to be able to handle all of the flow rate for the day, or for the instantaneous flow rate. Filters have to be handling water that is pre-treated. When the source water has to be pre-treated with chemicals before you filter it. The filter loading rate is going to be provided by the engineer based on source water quality, the degree of pre-treatment, and the competency of the operators. It's a very big deal, of course. And of course, demonstration studies can be used to determine what filter loading rate can be approved. And this plant in particular did do a demonstration study. Lake County Utilities did a demonstration study, which got the approval of a 5.7 gallon per minute per square foot loading rate. If the utility applies for those higher rates, then as standard, they must demonstrate that the configuration can provide at least 5,000 unit filter run volumes, and this plant did indeed prove that. Dual media filters has to be constructed along the following guidelines. For the sand, the effective size has to be somewhere between 0.45 and 0.5 millimeter, with a uniformity coefficient not greater than 1.65. You'll find later that this plant has a much more stricter standard than that it met. Specific gravity of the sand has to be 2.5 and at least 12 inches of depth. The anthracite that goes on top of that sand has to meet an effective size of somewhere between 0.8 and 1.2 millimeters, with a uniformity coefficient not greater than 1.7 when used as a cap. And usually 24 inches depth are needed, but can be demonstrated if you want to show less. When we look at disinfection, you'll notice intense state standards, one of the first phrases that you meet in heavy bold print is chlorine is historically preferred disinfectant. But plants in Ohio can use other disinfectants, including sodium hypochlorite, which we're going to concentrate on today because that plant uses that. And of course, you can use other forms of chlorine also. If you're going to have hypochlorite, the hypochlorite feeders must be of the positive displacement type. And each one that you have must be capable of satisfying the chlorine demand plus maintain a free chlorine residual of 2 milligrams per liter after 30 minutes. So after 30 minutes of contact time, you satisfy the chlorine demand, there still has to be 2 milligrams per liter after 30 minutes later. Standby equipment, of course, has to be available that can replace the largest unit in service. So typically that means you're going to have spare parts available. Usually a spare pump is advisable. And of course, these parts are subject to wear, so you need to have them on hand. When it comes to chlorine residual, the chlorine must not be less than 0.2 milligrams per liter in the distribution system, and the residual leaving the water treatment plant shall be greater than 4 milligrams per liter free residual. Continuous monitoring equipment, of course, is needed for chlorine residual as required, and analyzers have to meet compatibility requirements for EPA method 334 for chlorine residual. So we'll see if this plant stacks up to that. So let's look at the Aquarius water treatment facility, which again is a 20 million gallon per day conventional water treatment plant which uses Lake Erie as a source. This is the picture of the plant itself, and there's a unit processes that we're going to go through mostly today. Now, if we look at the process flow diagram for the Aquarius water treatment plant, we notice in the upper left-hand corner we have a remotely located raw water pump station that has 3 pumps at 8.55 mgd and another 2 pumps at 4.54 mgd. There's provision to add potassium permanganate at the wet wells. The water is pumped up to 2,000 feet of 36-inch water main, comes up to the plant, and splits in parallel to the west side and the east side of the plant. Each side has a mirror image of the other. There's a rapid mixer, 3 flocculators, and 2 sedimentation basins. And on the east side, there's the mirror image of that. So when water flows in that pattern, it's called flowing in parallel, goes through all of the basins, ends up in the settled water flume, where it's then taken across the administration building and heads over to the 6 filters on the east side of the northeast side of the building. So one of 6 filters or all 6 filters can be in service. They empty into the clear well storage, pump wells, where there are high service pumps and backwash water pumps. And of course, there's also a basin to capture spent filter backwash water and return it back to the head of the plant. Some of the things we got to notice that are interesting about this plant, going back to the left-hand side or the west side of the plant, we notice the settled water flume that you see blinking there. If I could put the gate in the flume, the settled water flume, I can force the plant to run in series. Everything would come through the west side of the plant, go through those 2 west basins, and come up the series flume up to the 2nd rapid mixer and go through the mirror edge of the east side. That would be called running the plant in series. When you run the plant in series, you have 2 chances of rapid mixers. You can do one thing in one rapid mixer and something else in the other rapid mixer. It can handle certain problems that are a very handy thing to have. However, when you do that, you double the flow-through velocity of the said basins, and so it's a little bit more difficult to settle flocculated material out because you're speeding the water up. You're doubling the velocity, so they have to be careful of that. Another thing to notice is the hypochlorite system. Hypochlorites are stored in a storage tank and clear well assembly on the left-hand side, and the big pumps that take that hypochlorite system and send it across to the filters are situated along this line here that's blinking. That hypochlorite is pumped from the pumps across to these 2 tables that you see blinking that have 3 pumps each dedicated to 1 filter. So one of those pumps runs to each filter that's in service and adds hypochlorite solution to the effluent line of each filter. So an operator can dial in the exact dosage of chlorine solution that he or she needs. Any hypochlorite that isn't used is then sent back to the day tank through that return line. So there's a continuous loop of hypochlorite solution being fed in that loop to the filters and back again. And the amount that is fed across that line and back again is much greater than can be used by any of the filters in service at any given time. So it's as if they're having a day tank on the east-hand side. So that's an interesting part of the system. Another thing you want to look at is on the left-hand side, you see that blinking drain there. Provision was put in this plant when it was built to allow for back flushing of the intake during times when the plant is down in service and you might have phrasal ice or needle ice. You need to back flush the main to clear out the ice jam. You can drop the You can open the basin and drop the head of the tank, the sedimation down through the intake and clear it out that way. Lake County Utilities participates in the Partnership for Safe Water voluntary program for excellence. So the Aquarius water treatment plant uses the software to generate a process capacity analysis graph or a performance potential graph for its unit processes. And you notice the graph here, the largest line you see on there is the one for flocculators, and the smallest one is for sedimentation basins. Notice there isn't one for rapid mix because the rapid mix of 30 seconds is so small compared to the other graphs, it doesn't show up. So the partnership doesn't really display a graph for that. So the graph reads this way. You see a black line going across at the 20 MGD mark, and each unit process is rated at its ability to handle that flow capacity. You notice that at that flow rate, flocculation capability of this plant would be well over 60 million would be able to handle, so they obviously don't need to have all their flocculators online. In fact, the smallest line you see is for sedimentation, and that's not unusual for a bigger plant like this. Engineers are going to design sedimentation basins at a bare minimum of 4 hours of detention time because they're very expensive to design and build. A lot of concrete there, a lot of metal, a lot of rebar, and so they're going to minimize that. In a smaller plant, you'd see the smallest line probably being the filters, because where you only have 2 filters, you take one out of service, you've lost 50% of your flow capability. That's probably going to be your smallest bar graph. So the operators know here that when they take a sed basin out of service, it's something they got to pay attention to from this graph. Notice that there's plenty of capability for disinfection. We start looking at the raw water and plant process description. We see that we start out at the source, coming through a 60-inch intake from Lake Erie through 31,000 feet of pipe. It sits in about 48 feet of water. At the max flow rate of 20 MGD, if you convert that to cubic feet per second, it would be 31. And if I do a velocity calculation, I take that flow rate divided by the square foot area, I come up with about 1.57 feet per second. As I mentioned before in other modules, engineers like to design water pipes to handle somewhere between 1 and 5 feet per second velocities. Anything lower than 1, you're going to have pre-sedimentation of organic material and some inorganic fines. Anything greater than 5 feet per second, you're going to have premature wear of the pipe. So this plant, the operators at this plant understand that because they're at 8 or 9 MGD most of the time, they're going to get some pre-sedimentation because the velocity through their intake is going to be less than, say, 0.7 or 0.8 feet per second. So that's something they think about, sending a diver down there every couple of years to make sure that everything's okay. They also have a screening process, and as I mentioned, permanganate feed, wet wells, and 5 raw water pumps. You look at the raw water pumping station, there's some pictures of pumps number 4 and 5 on the left, and pumps number 1, 2, and 3 on the right. And they're listed at 2 at 4.54 MGD for the small pumps, and those are 75 horsepower pumps. And the 3 big pumps are 8.55 MGD at 150 horsepower, all at 78 feet total dynamic head. Of course, pumps number 2 and number 5 have variable frequency drives installed on them. And if you look at the firm capacity, which Ohio EPA defines as the total capacity with the largest pump out of service, you can add those up. You see 2 of them at 8.55 plus 2 of them at 4.54. You come up with a firm capacity of 26.18 MGD, or approximately 18,200 gallons per minute. So if you wanted to do a horsepower calculation on one of the large raw water pumps that's operating at capacity, you do it this way. You take the horsepower would equal the gallon per minute times the head divided by the 3960. So I would take the 8.5 million gallons and divided by 1,440 minutes in the day and multiply by 78 feet divided by 3960, and I come up with a theoretical horsepower of 116.9. And if I assume that system is 85% efficient, I would take the 116.9 divided by 0.85, and I see that I'm only developing 137.5 horsepower, which is well within the range of the maximum of 150 horsepower that was designed for. So these pumps are not really having to operate full out. They should last quite a long period of time. There's the raw water station. There's some of their screens, process, and there's their permanganate system. You notice you have a day tank with a 300-gallon capacity. And they typically make the permanganate solution to 0.25 pounds per gallon. The original design called for a 1 pound per gallon solution, but we found out the hard way a long time ago that permanganate doesn't dissolve very well in the wintertime, and the pumps tend to get clogged up with granules of permanganate that sit at the bottom of the tank in the cold water that can't be dissolved. So always you want to make sure that you make a weaker solution for permanganate. It means you have to go down there more often to fill up the day tank, of course. Operators sometimes don't like that, but it sure saves them a lot of problems in the long run. Here's a speed control system that runs the pumps. At any given time, the milligram per liter dosage that's being fed can be determined by capturing the amount of milliliters per minute of permanganate falling into the wet wells, and you can be converted to dosage using those formulas that you see there. Now with that information I just gave you, if you wanted to do an example permanganate dose problem, it would look like this. Let's say they give you the raw water flow of 8.6 mgd, and the operator wants to feed 0.3 milligrams per liter potassium permanganate. How many milliliters per minute should be fed? Now you know from the previous problem, we're making the solution at 0.25 pounds per gallon. So with that, you might want to shut off the video at this point or pause it and do the problem for yourself. With that, I'm going to continue with the problem. I'm going to take the pounds per day needed is going to be 0.3 milligrams per liter times the 8.6 mgd times 8.34. I'm going to need to feed 21.5 pounds per gallon to achieve a 0.3 milligram per liter dosage of permanganate if the flow rate is 8.6 mgd. But I need to know the milliliters per minute I need to set the feeder at. So I'm going to take the 21.5 pounds per day divided by the 0.25 pounds per gallon. That'll tell me how many gallons per day I'm going to have to feed. I'm going to take those minutes in a day of 1440 and divide it into that figure, multiply it by 3,785 milliliters per gallon. I'm going to come up with a feed rate of 226 milliliters per minute. If the operator captures that in a test, he or she knows they're feeding the 0.3 milligrams per liter. So some things to know about the raw water system at Aquarius plant. Again, we have the 36-inch diameter main. All of that water has to come from that main at the raw water station up to the plant. So that's a critical point for them. They do have some waviness to the line. It goes up and down the hill a little bit. So there's some high points. And at those high points, they do have some air relief points. I've had the bitter experience myself of having to relieve air from those ports because you can't get enough flow through it sometimes. You know, if you shut the intake down for a couple of days to have to do some repairs, we start it back up, you find that the air has accumulated and you need to relieve that. So that's something to remember for plants like that. You look at the pre-treatment and post-treatment process description. There are 2 rapid mixers, 6 flocculators, 4 set basins, and 6 dual media filters. And again, the plant is rated at 20 mgd or 13.888 cubic gallon per minute, which works out to 31 cubic feet per second. The clear well and storage chambers have a 0.5 overall baffling factor. There's 2 clear wells, 2 subfilter storage tanks, and a pump storage chamber. So all those add up to be over 1 million gallons of storage. And you have 5 high service pumps and 2 wash water pumps that take water out of the backwash filters. In a conventional water treatment plant that uses coagulants and mechanical mixing, the operators are going to add this mechanical energy to the water to improve the coagulation and the flocculation process. The energy input typically is going to be had through the use of motorized agitators or impellers. And those impellers are going to be mounted on a fixed volume tank, such as the rapid mixer or the flocculator. Now the energy input into the rapid mixer, the G value, is going to be relatively short, but very violent. Here we're making small flock particles being formed. They're initially very fragile, so we can't stay in that rapid mixer compartment very long. So we got to be in and out very quickly, usually less than a minute on average. In Ohio, again, 30 seconds or less. The energy input into flocculators, on the other hand, is going to be relatively low but longer in duration. Typically, we're going to taper that energy as we go along the flocculator from one compartment to the next. Here, you know, we have particles that we formed in the rapid mixer are starting to collide with one another, and we want to provide more opportunities for collision so that these things start to stick to each other, grow in size, and typically we want to be there 45 minutes or less. As these stable colloidal particulate contaminants pass through these processes, they become destabilized and are conditioned properly for settling and then eventually filtration. We mentioned that in rapid mix, the goal is to quickly intersperse the coagulant into the raw water stream. There are 2 units at Aquarius plant, 2 rapid mixers. Each of them are about 676 cubic feet or a little over 5,000 gallons each. So the detention time with both units in service at 10 mgd would be 87.2 seconds, and at 20 mgd would be 43.6 seconds. So we can see that Aquarius plant, the operators rarely run two rapid mixers. They don't need to have that much rapid mix time. So one will do for most of their flow rates. Now each rapid mixer has one motor with one shaft, and there are two impellers on the shaft. Water comes into the bottom of the mixer, goes up past the first set of impellers, and then the second impeller on its way to the flocculators. The basins themselves have 4 redwood baffles, one at each side, and so when the rapid mixer revolves, the water has to hit up against those baffles and back mix. Very good arrangement for rapid mixers. So here's a picture of one of the rapid mixers. You can see the mixer motor assembly is providing a warm water G value of approximately 700 seconds to the -1. And we mentioned earlier that EPA now requires at least 750 seconds to the -1. This plant was built in 1985. When you have rapid mixers with agitators, they should always be operated, of course. You see also the provision to feed chlorine and caustic. You see those lines coming in the right-hand side. Remember, operators here have to add enough coagulant to remove 25% of the incoming TOC, and of course also to remove turbidity. And unlike most Lake Erie water treatment plants, more coagulant is needed to take out TOC than is needed to take out turbidity. So we want to talk about the processes of stabilization and destabilization and discuss how these two terms are used in conventional water treatment plant. These are terms that scientists use to describe the rates and the effectiveness of particle aggregation and floc formation. And if you look at the quote of the water quality book, it says, the object is to transform a stable suspension, that is, one that is resistant to aggregation or attachment to a filter grain, to an unstable one. Now that quote, which you found in the AWWA water quality textbook, is supposed to tell us operators that the bad stuff that we find in lakes and reservoirs has been there for a long time. It exists in a colloidal state, which are stable and discrete units that tend to stay in suspension and won't settle out on their own unless we do something about it. It's very stable suspension of particles. So we're going to try to destabilize that. We're going to do that by mixing in a coagulant. The coagulant will destabilize the aggregation, encourage these particles to start to stick together, and in doing so they grow bigger. They're going to be able to be settled more efficiently and filtered. So we do that by mixing the coagulant into the water, and when you do that, we use G values to determine how much energy it takes to do that. So again, as operators, we don't need to have that engineering level of understanding of G value, but there's a few things we probably ought to know so that we understand what they're giving us here. In conventional rapid mixing, G values are normally going to be in the 700 to 1,000 range, and again, as I mentioned, Ohio's got to be 750 or greater for new basins. So the older water plants have lower G value mixers, of course. They were designed at a time we didn't understand the effect of mixing on very small particles like we do today. So water treatment plants that were built in the early 80s, mid 80s, are usually equipped with higher G values than they were back in the before the 1980s. For conventional flocculation, G values may typically be at 100 at the entrance of the flocculator and taper down to 10 or 20 in the final compartment. Now, if your water treatment plant has variable mixing capability in flocculation, all of the operators should understand how to use this because it's one of the more valuable tools you use to optimize your pre-treatment process. So each operator should have a good working understanding of how many flocculators they have in service and how to taper the energy. So what parameters do we need to know about when we want to calculate a G value for a rapid mixer? Well, we look at the G value formula and we see that it's a function of several different things. Number one, it would be the volume of the mixer box, which we're going to designate as V sub T, or the volume of the tank, and that's going to be in cubic feet. We need to know the density of the water, which can be taken as 62.4 pounds per cubic foot. We're going to designate that as W in our formula. We need to know the number of revolutions per second of the mixer. They usually give it to you in RPM, so you're going to have to divide by 60, and that's you're going to designate as N in your formula. We need to know the diameter of the impeller in feet. We can designate that as a D. We need to know the value for gravity, or G, and that's fixed at 32.2 feet per second squared. We need to know the viscosity of the water, and we can look that up in tables. That's going to be given a micron symbol, or U, That's going to range from around 3.23 times 10 to the minus 5 at 40 degrees Fahrenheit. That's, of course, cold water, all the way to 1.88 times 10 to the minus 5 at 76 degrees Fahrenheit. And we need to know the power input of the mixing system. Of course, that's affected by several factors, such as the size of the motor, the number and angle of the impeller blades, and the number of revolutions per second. Of course, everything is fixed here except number 6, which is the viscosity of the water. We designate that as U. And again, that ranges from the 3.23 to 1.88. So that varies depending on water temperature. And that's what makes the difference in G value from cold water to warm water. So here's an example of those values put into our formula. And you see the formula for G value of the square root of the power divided by the viscosity of the water times the volume of the tank, where the power, or the P value, is the top value, which is the K divided by G multiplied times W times N cubed and D to the 5th power. So all those values put on. You see they are all the same values except for the 2 different U values, or viscosity values, that I put there. And on the right hand side, I've done a calculation showing you the water at 70 degrees, showing you a 710 value, and the water when it's cold at a 524 value. So the G value gets lower as the water gets colder, and that makes sense because the water is more viscous, as I mentioned, in cold water, and so the value changes. Now at the Aquarius plant, they use the alum polymer blended coagulant, and they express their dosage as milligrams per liter total product. So when they make their rounds and check the dosage from time to time, they capture the amount of chemical being fed right into the rapid mixer for a minute and determine milligrams per liter dosage from that. And of course, they're trying to feed enough to meet the Partnership for Safe Water goal of 0.1 NTU all the time coming out of each filter. So it's a 3-step process. They have a reason for choosing their dose. We've talked about this before, a jar test or some seasonal experience. Then they have to take that dosage that they've chosen in the testing and convert it to the actual feed rate of the pump. And then in the 3rd step, they got to make their rounds to determine if that's actually being met. And if not, of course, they make adjustments. Now, this is an interesting slide that I borrowed from the Partnership for Safe Water. Why does the Lake County water plants and other plants that join the partnership have a goal of 0.1 NTU in the finished water at all times? When you look at the slide in the upper left-hand corner, you see the microscopic particulate analysis picture of water at 0.3 NTU versus water at 0.1 NTU. If you're a water plant operator, or if you're a consumer, which of these 2 waters would you rather deal with? The water coming out of the filter at 0.3 NTU or the one at 0.1 NTU? Clearly, the partnership goal of 0.1 is something that most operators want to reach. Lower right-hand corner, you can see a graphical display of cyst removal as a percent versus effluent turbidity. And we can see that the lower the turbidity on the left-hand side, the greater percent removal we get of cysts, and that's something worth shooting for. This is a picture of the 3 coagulant pumps at the Aquarius water treatment plant. Remember, each one of these pumps has to be able to handle all the load at any given time. The other 2 would be in standby, and of course they rotate these pumps from month to month to month to be sure that they're always working in good order. Here's a coagulant dose example. Let's say the flow through the plant is 8.7 mgd. The operator makes a coagulant feed check by allowing the feed stream to drip into a 1,000 milliliter graduate cylinder. After 60 seconds, the operator notes that 560 milliliters has been captured. We know the product weighs 10.8 pounds per gallon. What's the dosage in milligrams per liter? And you'll find that on the next slide. You may want to stop right now and work this out for yourself and then go on to the next part of the video. The answer, of course, would be to calculate the amount being fed in pounds per day, and that would be the 560 milliliters per minute divided by 3,785 milliliters per gallon times the 1,440 minutes in a day and the fact that the product weighs 10.8 pounds per gallon. So that's going to show you that you've used 2,300 pounds per day of liquid coagulant. You can convert that to milligrams per liter by taking the 2,300 pounds per day, dividing it by 8.34, and the flow rate of 8.7, and it comes up to 31.7 milligrams per liter product. And then we move on to flocculation. Now, flocculation, of course, is a physical process. The flocks that we formed in the rapid mixer are now being allowed to collide gently and frequently in the flocculator. If they collide frequently enough, they're going to begin to stick together, and of course they're going to grow in size. And so that's what we want to have happen because they become more dense and heavier, and they're going to settle out in the sed basins properly. Now, flocculation, of course, follows coagulation, usually takes place in a chamber that provides a slow, gentle agitation of the water. In the flocculation stage, physical processes transform the smaller particles of floc formed in the rapid mixer into larger aggregates of floc. This rate of aggregation, this floc formation, this rate, is determined by the rate at which the particles are going to collide. So the more opportunities you provide for collision, the greater the rate of aggregation. As these aggregates go in size, they become more fragile, so the mixing force that you put into the flocculator has to be tapered down the further you go into the flocculator. So you do that typically in a plant like this by having less and less paddles as you go along the flocculator. So the speed of the paddles in the final flocculator stage is going to be very important, and they have to be controlled to produce the best floc possible. This is a picture of the flocculator area in the Aquarius water plant. Remember, the goal in flocculation is to take the newly formed floc particles and allow them to grow in size by providing collisions. They have 6 units. They're each at 4,080 cubic feet, or about 105,000 gallons each. So if you look at the detention time with all of their flocculators in service, at 10 mgd it would be 90 minutes, and at 20 mgd it would be 45 minutes. So they obviously have plenty of flocculation time, and we saw that on the Partnership for Safe Water graph. Each flocculator has 1 motor and 1 shaft and 4 compartments. In these compartments, in the first compartment you have 4 paddles, 3 in the second, 3 in the third, and then 2 paddles in the last compartment. So the G values are typically about 70, 50, 50, and 20 seconds to the -1, although those can be tapered, of course. Those can be challenged. Now this is how the flocculator compartment looks at Aquarius plant. This is how engineers design these. So basically, here's a compartment with one compartment, 4 different zones, and 4 sets of paddles in the first zone, 3 sets of paddles in the second, 3 sets of paddles in the third, and 2 sets of paddles in the last. So water coming in the left-hand side would come into this compartment, and most of it would shoot down through the middle and come out the other end of the flocculator in a time shorter than the theoretical detention time. If Ohio wants you to be in there, say 30 minutes, and you had no baffling in these compartments, water would shoot down the middle, and some of it would escape sooner than the 30 minutes, and some of it would take longer than 30 minutes to get out. The idea of a flocculator is to try to force all of the water to stay in there as close to the 30 minutes as possible. Now, how do they do that? They do that by putting in compartments. So now, when the water enters the flocculator, it's got to go down underneath the compartment in the first thing as it goes through the paddles, come up under the second set of paddles, go up over the compartment baffle wall, back into the third compartment, and up over the wall, in the fourth compartment, and over to the sedimentation basins. In doing so, it has to take a more snake-like path, and so it travels a longer distance. By traveling a longer distance, more of it is forced into a plug flow arrangement, so more of it stays in there closer to the theoretical detention time of 30 minutes. There's less short circuiting, and that's what the engineer wants to design. Now, the engineers have this design arrangement down pat when it comes to compartmentalization in flocculators. If you look at this graph here, this shows you retention time of actual to theoretical on the bottom part of the graph, and then in the upper portion of the graph, the vertical axis, proportion of flow rate retained less than the stated amount of theoretical detention time. And here's how this graph works. Let's say I do a theoretical detention time at any given flow rate that I have going through my plant, and I have a flocculator with only 1 compartment, so it's got no baffles in it. Let's say I take that 30-minute theoretical detention time, and I call that a unit of 1. I'm going to put my circle right there at the 1 unit. And say if all of the water stayed in at that ratio of 1, all of it would be in at 30 minutes and then come out the other end in exactly 30 minutes. But of course, in a flocculator, we know that doesn't happen. If I took a theoretical amount of detention time of 30 minutes and asked myself, what would happen in 15 minutes, just half of the time that I was there? I'll put a bar on the graph at 15 minutes, and I would see that if I have only 1 compartment in my flocculator, 42% of the water would escape the other end of the flocculator in less than 15 minutes, or half of the theoretical detention time of 30 minutes. I wanted my water to be in there 30 minutes to get proper flocculation, and I see that half of it has already escaped before 15 minutes is up. I have to put some baffles in there to stop that from happening. If I put 3 baffles in, 3 compartments, make 3 compartments out of my flocculator, now I can improve my situation such that only 22% of the water escapes in less than 15 minutes. That's much better than the 42%. At Aquarius plant, they have 4 compartments. So we notice that for them, only about 17 or 18% of the water is escaping in less than half of the theoretical detention time that I want that water to be in there. So that's good. But of course, that also means that some of the water is staying in there a lot longer than the 15 minutes. And if I have too many flocculators on, I can be in there a lot longer than I need to be. So the Aquarius plant operators know that they don't need to use all of their flocculators. In fact, that can harm them if they have too many flocculators online. They typically are only going to run 2 or 3 at the flow rates that they're at. The final tip speed of the last paddle in the final compartment of a flocculator has to be somewhere around 1 foot per second. And the operator has to do a calculation to determine just what that distance is and time is. So when that outer paddle travels around one time, if it has a 12-foot diameter, the distance that it's going to travel would be pi times the diameter, or 2 pi r. So the circle of travel that it cuts out by going around one time would be its circumference. And the operator needs to know that at 1 foot per second, how long it's going to take to go around that distance. So if I want to look at example tip speed calculations at Aquarius, I have to realize that the flocculators here, of course, have the 4 compartments, one central shaft that rotates and drives the paddles. The distance from the middle of the shaft to the outside edge is 6 feet. That would be the radius, so the diameter is going to be twice that, or 12 feet. So if I wanted to know how much time the last compartment should take to make one rotation, and I'm traveling at 1 foot per second, how do I do the math? The outside edge of the paddle rotating on the shaft will cut out a circle that has a perimeter of pi times the diameter. That's going to be 37.68 feet. So if I'm traveling at 1 foot per second, it should take me 37.68 seconds to make that revolution. This is a picture of the variable speed drive that drives the paddles. It sits down in the basement of the flocculator room. Operators can go to that machine and vary the speed of the paddles by working with the mechanism itself. Flocculator drive settings are found here on the dial, and within the span of 0.2 to 0.8, the mechanism will drive the shaft at about 1.22 to 3.65 rotations per minute, and that of course corresponds to a tip speed of 0.76 up to 2.3 feet per second. So the operator is typically going to be found to put the bar at about 0.3 to 0.4 setting there. They're just going to drive the paddles at about 1 foot per second. Of course, moving on to sedimentation from here, we understand that sedimentation is a solid separation process. And in a conventional water treatment plant, that process is going to allow the major part of the flock that we formed to settle out in the basin. Of course, that flock is going to come from the raw water particulates that come in and the coagulant that we add to the water. Those are the 2 major sources of the particulates that we're going to try to settle out. Sedimentation relies on gravity, and of course temperature is going to play a role. The colder the water is, the harder it is to settle the water out. So we also have to realize that basins are going to accumulate the majority of the sludge that we produce. Most of the particles are going to be taken out here, so that sludge of course has to be taken away periodically. Looking at sedimentation at the Aquarius water treatment plant, we see that we have 4 basins, each of them 112,955 cubic feet each, or that works out to about 845,000 gallons each. The surface area of each of these basins is 7,790 square feet. The detention time with all basins in service at 10 MGD would be 8 hours, and at 20 MGD, of course, the 4 hours that was required to be designed into them. Design surface overflow rate is 0.445 gallon per minute per square foot, or about 1.85 centimeters per minute. They have V-notch weirs. There are 8 weirs per basin, and these are double-sided. Each of them is 17.4 feet in length. So the total weir length then would be the 17.5 times 2 sides, times 8 weirs, times the 4 basins, or 1,120 feet with all basins in service. So the design weir overflow rate would be 12.4 gallon per minute per foot, or 17,856 gallons per day per foot, which all meets Ohio EPA standards. So here's an example. Calculate the weir overflow rate if you have 3 basins in service and the plant is treating 12.4 MGD. So you have 1 basin out of service for maintenance, say. Do I have enough overflow rate? Do I have sufficient overflow rate on the rest of them? You take the 12.4 MGD, divided by the 1,440 minutes, you get 8,611 gallons per minute. And divide that by 3 basins, and the weir length of the 3 basins, you come up with 10.25 gallon per minute per foot. Remember, the goals for settled water turbidity should be less than 1 NTU when the raw water turbidity is less than 10, and should be 2 NTU or less when the raw water turbidity is greater than 10. When we look at the issues for sedimentation basins at the Aquarius plant, we have to remember that these were designed for parallel and series operation. So there are some issues that we have to deal with, and operators need to remember this. They look at the flow-through velocity. And remember, Ohio EPA says the flow-through velocity should be 0.5 feet per minute or less. If you calculate that at Aquarius plant at 20 mgd, it's going to be V equal Q over A. You're going to take the 20 mgd, convert that down to cubic feet per second, and divide it by the surface area of the face of the basin, not the top surface area, but the face of the basin, which is 41 feet across and 14.5 feet deep times the 4 basins. You come up with a 0.78 feet per minute, which is higher than the total 10 state standards guideline. So when the plant is put into series, this can be an issue because the velocity doubles to 1.56 feet per minute. So operators should always remember that this velocity may be critical to their thinking depending on the reason for going to series flow. Past experience with series flows always produce higher basin NTUs going over to filtration. Sludge basin maintenance at any water treatment plant, of course, is always a difficult issue for operators. But basins, of course, have to be taken out of service once in a while for cleaning, inspection, and maintenance, and it has to be done on a regular basis. It's a duty that most operators don't enjoy, and some, of course, try to avoid it, but it has to be done. Old sludge accumulates in the corners and on piping and on walls and things like that, so the walls need to be blasted with high pressure hoses. The biofilm that grows on them has to be cleaned away. You may have sludge collectors in place, but they can't get to all of the sludge and all the biofilm, so occasionally you have to take these basins out of service and clean things up. Okay, moving on to filtration. Filtration in the water treatment industry, of course, is a solid separation process, just like sedimentation is. Again, unwanted contaminants in the water are going to be physically removed when we pass the water through, in this case, granular media filters. And in a dual media filtration process, we have 2 medias of different specific gravity, one placed on top of the other, which all sits on top of a porous plate bottom that allows the water to pass through. And by choosing larger grains of less dense media that rest on top of the filter, the flock will penetrate deeper into the bed and allow for longer filter runs. And we mentioned earlier that there are 6 filters at Aquarius. Each of them are double-celled. In each cell, each half of the filter is 468.5 square feet. So when you add the 2 halves together, you get a total surface area per filter of 937 square feet. Now this configuration was rated at 5.7 gallon per minute per square foot. So if you take the total square feet of a filter, multiply it times the 5.7 gallon per minute per square foot, you see that each filter is worth about 5,337.5 gallon per minute, or about 7.68 million gallons per day. So that works out to quite a bit of filtration capacity, but the existing piping limits the filters hydraulically to 5 gallon per minute per square foot. So practicality exists for filtration at Aquarius plant at 5 gallon per minute per square foot times 2 halves times 468.5 square feet. Each half comes out to about 33.7 million gallons per day. Much more capacity than they really need because, again, this is a 20 mgd plant. Now for backwash purposes, when a filter is taken out of service, each cell is backwashed separately, allowing you to have smaller backwash pumps. Each pump is rated at 9,800 gallon per minute, and there were 200 horsepower pumps at 56 feet total dynamic head. So the wash water rate would be 9,800 gallon per minute divided by the half of a filter, 468.5 square feet, or about 21 gallon per minute per square foot maximum capacity. This is an aerial view of the filtration plant, the Aquarius plant. You notice that the left-hand side, upper left-hand corner with a pre-treatment system going into sedimentation basin, filters over on the right-hand side. They also have their distribution garage on the property. Looking at the layout of the filtration building, we see at the top floor we have filters 1, 3, and 5 on the west side, and filters 2, 4, and 6 on the east side. North, of course, is going up to the top. If we drill down in a little bit, we see that the 3 west filters sit on top of a 375,000 gallon filtered water storage basin, and filters 2, 4, and 6 on the east side sit on top of a twin basin, same size, 375,000 gallons. Those things that are blinking are on the top floor. You see that the high service pumps sit there up top, the pump chambers, and the 6 hypo feed pumps. Those filters on the west side empty into the opposite east fluid water storage reservoir, and vice versa, the filters on the east side empty into the left reservoir, western reservoir. The reason they did that is to get enough length for straight pipe coming out of the filter to be able to put a flow meter in there and not have turbulence coming into the flow meter so they get accurate readings. So they need enough straight pipe that can serve space. Again, these filters are highly rated dual media filters. There are 24 inches of 1.1 millimeter anthracite with a small uniformity coefficient sitting on top of 12 inches of 0.5 millimeter effective size sand, again with a small uniformity coefficient. That all sits on top of 8-inch IMS cap under drains, and again they have a loading rate for the configuration of 5.7 gallon per minute per square foot. So this is depth filtration, and they have a lot of headspace for washing, and that's the reason why they went in with this configuration, so that they get enough headspace for backwashing. We look at the dual media characteristics of the 6 filters at Aquarius plant. We're going to look at the L/D ratio calculation. Remember that L/D would be the depth of the bed in millimeters divided by the effective size in millimeters, and that value of both layers of the sand and the anthracite added together should be greater than 1,000. So when we do the calculations for L/DE ratio, we'll do the sand first. We'll take the 12 inches of sand and we'll convert it to millimeters by multiplying by 25.4. We'll divide that by the effective size of 0.5, and I'll come up with a value of 610. We do the same thing for the anthracite. We'll take the 24 inches of anthracite and multiply it by 25.4 millimeters per inch. Divided by the effective size, we come up with a value of 554. And remember, these values are additive. When you add the two of them up to get a total L/DE ratio, we'll take the 610 and add it to the 554. We'll come up with a value of 1,164, which is much greater than the 1,000 that is needed. This gives the operators a cushion. They can afford to lose an inch or two of media over the years, which is natural through backwashing, and lose some fines over the years. They'll still have a value greater than 1,000. The intermix ratio calculation is also very important. We remember when we do that from previous modules that we've done, we wanted to take the D90 coal size and divide it by the D10 sand size, and that ratio should be somewhere between a 3 to 3.5 for a good dual media filter. When we do these numbers, we take the D90 size of the coal, which was 1.669, divided by the D10 sand size of 0.514, we come up with a 3.25, which is right in between that value of 3 to 3.5. And we mentioned the flow rate meters that had to be placed in line, so we needed a lot of straight length of pipe coming out of the filter. So we had it discharging into the opposite clear well storage basin. This is the magnetic flow meter that was put in line to the filter effluent of each filter. And this signal that comes from this meter is a flow pace value that paces the hypo feed. From there, we go on to disinfection. Of course, in the water treatment industry, disinfection is going to refer to the chemical or the physical inactivation of the pathogens that we find in our public water supplies. Usually it's going to involve some type of cell disruption that's going to harm the pathogen and kill it. That can be accomplished either by using some chemicals like chlorine, chloramines, ozone, chlorine dioxide, other kind of chemicals, or it can be a physical process. Physical disruption can be accomplished by UV disinfection, ultraviolet disinfection. No matter which way you use, in Ohio, you are required to have a residual of chemical for the distribution system, so typically that's going to be chlorine anyway. So the Aquarius water treatment plant uses liquid hypochlorite for disinfection, and typically it's supplied in bulk at about 12%, and they get a truckload in and divvy it up between the two water treatment plants they have, most of it going to the Aquarius plant, the other going to their smaller plant, the Bacon Road water plant on the east end. They have a hypo storage tank and day tank at the Aquarius plant that I showed you in the diagram earlier. And they have the dedicated peristaltic pumps that move the hypo solution to the flume and to the other across the tunnel over to the filter building, as I showed you, to the filter tables that have the individual feed pumps. So disinfection, of course, is regulated by the Interim Enhanced Surface Water Treatment Rule, which requires proof every day that adequate disinfection has taken place. To do that, you have to do a CT calculation. That's done every day, finding the worst case scenario for each the previous 24 hours, and you report that. Also, you have to have a residual disinfectant that's maintained in the water plant and in the distribution system. So operators have to measure the plant tap residual. That's monitored continuously. And the distribution system has to be monitored when you take bacteriological samples to make sure that meets certain standards also. Again, for disinfection at the Aquarius plant, they use the hypochlorite system. And of course, the hypochlorite is stored at the chemical building on the west side of the plant in both a storage tank and the day tank. And at that situation, there are oversized positive displacement pumps that move the hypo in that continuous loop along the passageway from the west side of the plant over to the east side where the filters are, and then back again. So there's a continuous loop operating, and the 6 smaller dedicated pumps at the filter gallery take their supply from that continuous loop and feed it to the respective filters as needed. So any hypo that is not used, of course, remains in the loop and just keeps circulating. So there's always a supply of hypochlorite coming to the filters. Now, each of those 6 small hypo filters is controlled by the filter effluent flow signal, which we showed you in the previous slide. Calls for the hypo as needed. The filters discharge into the dedicated flow pipe and then into the opposite filtered water storage chamber, as we showed you. This allows you to control the rate of flow of the hypo using a valve and a pump arrangement. Very precise control of the hypochlorite feed. All the operator needs to do is build in the dosage that he or she wants and the strength of the chemical. This is a picture of the hypo day tank and the feed lines with the return lines. Again, the hypo that they use is generally between 12 and 15%. Stays pretty stable in this arrangement. These are the main hypo bulk feeders on the west side by the day tank. The main feed pumps are 10 to 25 gallon per hour Watson-Marlow model 620 DUSRE peristaltic pumps. They feed a quantity of hypochlorite through the continuous loop. The smaller pumps on the left-hand side, the 2 small green ones, can be used to feed hypochlorite to the flume prior to filtration if needed. And they typically do feed a little bit of chlorine on top of the filters to maintain filter disinfection. This is the hypo system located in the filter area, the 2 tables with 3 pumps each on them. The continuous loop brings the filter chlorine over to the filter building, and back to the day tank. Constant pressurized flow to that area, and the 6 peristaltic pumps take suction from that flow. So again, this is a flow-paced system, and each will feed about 4.5 gallons per hour to the filter. More than that is adequate than is needed for the filter. So if you want to look at some simple steps to calculate the actual dosage hypo being fed to a filter effluent line, let's take an example here. We'll look at a filter flow rate of, say, 2,150 gallons per minute. Again, this is an individual filter. And let's say the operator is feeding hypo at 12%. The math would look this way. I'm going to take the filtered water flow in gallon per minute multiplied by 3.785 to contain liters per minute. So as an example, if I take the 2150 gallon per minute multiplied by 3.785, the filter is putting out 8,137.75 liters per minute. So I read the amount of hypo solution that's being fed at the feed pump in milliliters per minute to that flow rate. Say it as an example, the pump is feeding 142 milliliters of hypo in 1 minute. We know that the chlorine is 12%, the hypo is 12% hypochlorite. I can calculate the dose this way. I can take the 142 milliliters per minute, multiplied by the fact that it's 120 milligrams per milliliter, and divided by the filter flow rate, and I come out to about 2.1 milligrams per liter chlorine being fed. When we spell out the regulatory requirements for disinfection, we see that a minimum amount of disinfection sufficiency has to be met each hour by applying enough chlorine to the water to establish what we call a CT value that provides 1/2 log inactivation of viruses. This is after filtration, of course. The CT value, or the concentration of the chemical times the time that it's in contact with the water, has to be multiplied by an assigned baffling factor of the clear wells and storage cells, which for Aquarius plant is 0.5. In other words, EPA is saying, whatever volume of water you have in there, we're going to give you half of it as credit, which is pretty good, by the way, half a credit. And that's going to be multiplied times the free chlorine residual of the water in the clear wells at the lowest level and at the highest flow rate going through those wells. And this calculation has to be done each hour to assure that the CT value is being met. So when you think about it, the CT calculation is really done after the fact. Whatever happened the previous 24 hours, the superintendent comes into work and does a calculation to see that he or she met the CT value the previous day. The regulations also specify that the chlorine residual that leaves the plant can be no less than 0.2 milligrams per liter free residual at all times. This comes from section 3745-8172 of the disinfection of water from surface water sources here in Ohio. Chlorine residual, of course, has to be recorded continuously. using an approved measuring and recording device. And if this device goes out of service, it can't be out of service more than 5 working days, during which time the operators, of course, have to do chlorine residual recordings manually. Chlorine residual in a distribution system can be no less than 0.2 milligrams per liter free residual in 95% of the samples taken each month here in Ohio. So we can look at an example CT calculation by looking at this made-up arrangement that I put together here. This is not Aquarius plant, by the way. This is just something I made up just for illustrative purposes. Let's say you have a clear well that's 44 feet long and it's 30 feet wide, and it's split in half with a baffle coming in the side, and the inlet piping shows that the water comes in the topmost portion of the basin. We're looking down at this basin, by the way. So it comes in and goes through some baffling arrangements and comes around the one side and goes back down the other side. And the wall is 15 feet along, so the total distance, the total width of the basin is 30 feet. It's split in half at 15 feet each. So by the time the water comes out the other side, it's achieved a baffling factor of 0.5. So that's our arrangement for the CT example. So to do the calculation, we have to look at the operating data to determine what the lowest CT value was for the previous 24 hours. So the superintendent would come in and look at this table and see that for each hour, the operators had made their rounds and recorded the depth and the chlorine residual and the flow rate going through those basins. So every hour starting at midnight, 0, 0, 100 hours, you see that the first reading was taken at 11-foot depth, chlorine residual of 1.5 milligrams per liter, flow rate of 220 gallons per minute. So the superintendent would go through and determine what the worst case scenario is. In this particular case, it seemed to be 1,800 hours because the depth had dropped to 8.3 feet. Chlorine residual was at a low point of 1.6 milligrams per liter. The flow rate was 300 gallons per minute. Now you could argue a little bit that at say time 2000, the chlorine residual dropped to 1.5, but the depth was deeper and the flow rate was different too. So the superintendent chose in this particular case, the 1,800 hours is the worst case example. So when the superintendent did the calculation from the previous slide, find the worst case scenario, which hour had the lowest disinfection sufficiency. It shows the 1,800 hour mark because the flow was the highest and the residual and the clear well level were lowest. So the CT value in milligram minutes per liter would equal the detention time multiplied by the chlorine residual multiplied by the baffling factor. So to do that calculation, I multiplied the width times the length times 8.3 feet deep and converted that to gallons by multiplying by 7.48, and I see that I had 82,345.82 gallons. So the detention time divided by 300 gallons per minute come up to 274.5 minutes. So to calculate CT, I took the detention time, multiplied by 1.6 milligrams per liter and 0.5 baffling factor, and I come up with 219.5 milligram minutes per liter, which is much more than they need. Typically on Lake Erie, you would need about 8 to 10 milligram per liter minutes in the summertime and maybe about 70 or 80 milligram minutes per liter in the wintertime. They have way more than is necessary here. And that brings us to the end of our video. So we'd like to acknowledge again our thanks to the Lee County Department of Utilities and the Aquarius Water Treatment Plant for the use of their data and plant pictures. Hopefully this video will help you with the modules that we put on previously. Some of you had asked for this video, so this gives you an overview of the Aquarius Water Treatment Plant. Remember, you can click on some of the links that are scrolling up to bring you to these over 30 videos that will help you prepare for your exams. If any of you have any questions, remember you can reach me on YouTube. You can reach me at LinkedIn. You can reach me at Twitter, or email me at nick@aqsrv.com. Good luck with your exams. Thank you.